weren't able to be here. So, okay. So, ready when you are.
Yes. So I was doing it off of a calculation you had. Is this one that we calculate or one we ask M plus to calculate?
This is one you could just calculate yourself.
Yeah. So I thought I was doing it right, but I'm not. So I'm trying to find the exact example.
So question 39. At what theta value is there a 50% probability of answering a 2 or higher? Is requiring you to find the right submodel and then convert it into the version of the parameter that would give you the theta value needed. So this is one that M plus does not give you directly.
Okay.
So it's going to be related to thresholds and difficulties.
Yes. So I was on slide 9 of
Which lecture?
let me see. The last one.
The last one, lecture 6. Let me pull that up. So we're doing homework
That's where I was
questions,
getting
folks.
it from, and I thought.
Sorry, I'm narrating for those who are just popping in from the waiting room. We are doing lecture or pulling up things to answer homework questions. So if you have homework questions, please let me know in just a second. Come on, you can do it. So you said you're on slide 9?
Yes, which may as be the wrong slide completely.
This slide is not going to give you directly the correspondence between thresholds and difficulties, which is what that question is asking about. So that is given in a couple different places. It's given in the inside the M plus code in example 6a. It's also given in lecture 5. There's the conversion formulas. More generally, if memory serves, difficulty is threshold overloading. Does that sound right?
Yes. And I also did that and I got the wrong answer. So I don't know if I'm just completely doing it
wrong. I may have to, yeah, I may have to see what you're referring to, but just keep in mind answering 2 or higher. Make sure you're in the right submodel.
So, yeah. Actually, I did 40 first because I thought that would be easier. And then if I got that right, I would go back to 39. Because I think that 40 is more intuitive for me because a lot of what we do, it's theta at 0. So I was like, let me just do that because I have less chance to mess it up. I was still getting that one wrong. So I really didn't even try 39.
The other is, are you in the right model? So this.
I mean, everything else is correct. So everything 41 I got correct, 38 through 31 I got correct. I just am stuck on 39 and 40.
Okay, I may have to look at what you think you're doing more specifically and help on that one. But it sounds like you're in the right neighborhood. So hi folks, we're talking about homework 4, which is due on Thursday. So any questions I can help you guys with? I looked at the database a few hours ago and I know that not everybody's done yet. So Thursday, end of night, 11:59 p.m. Just as a reminder, late homeworks have a 1-point deduction, but you can submit them anytime. So if it takes you longer and you're willing to take the point deduction, that's okay with me. At the beginning of the semester, you all earned 3 points extra credit for doing homework 0. And this pandemic semester, the penalty for late work is much less. It used to be 3 points per assignment, and I've dropped it down to 1 because life is uncertain right now. So office hours today as well, if anyone wants to come by and work on that. So no questions? Okay, fair enough. Then let me point out change to the syllabus that I made. So we're in week 12, if you can believe it. approaching the home stretch. And as we discussed last week in class, on Thanksgiving week, there are no classes meeting that week, but I have decided to hold office hours during the hours I would normally be in class because you have homework 5 that is due the Monday after we return. So from 12:30 to 4:45, the Tuesday of Thanksgiving break, I will just sit here and hang out with my Zoom room open. And if you all want to take your vacation and not come and talk to me, that's fine. But if anybody wants to ask questions, I'll be here. I can always find things to work on if nobody shows up. I won't be offended, but I thought I'd give you the chance. Everywhere else that I've worked, we had classes on Monday and Tuesday of Thanksgiving week. So this is sort of weird to get the whole week off, but that is what it is. And we have a bunch of new stuff to talk about invariance this week and next. So are you ready to start some new stuff? Yes, T is excited. Yes. So one of the things that, let me pull up my lecture 7 here. Here we go. Let me move the thingy out of the way. There we go. I get at least one email a week from someone I've never met who found my stuff online and wants to say thank you for putting all of my class material online. And oh, by the way, I have a question. Can you help me? All of the emails sound like that. And by far, even though this is not my area of expertise, by far the most questions I've gotten is about testing measurement invariance in M+. For whatever reason, these handouts have resonated with people in a way that I would not have anticipated. So if anyone out there is watching, hello, strangers. Welcome to class. This is not my area of research, but I have figured out how to make M+ do my bidding. So apparently for that, I win, and you all will win too. So I have a combined lecture to describe the process of testing measurement invariance, which is what it is called in the framework of confirmatory factor analysis models, as well as differential item functioning, which is what it is called in the context of item response theory models. Same set of concepts, not the same words, and very similar process though for testing them, at least within M+. And by the way, there is a whole nother set of research that didn't exist until fairly recently about how to do this process across lots and lots of groups. There's an article on your reading list about that. So I just wanted to make you aware that there has been some new developments in this literature since I started teaching it. So first off, some words here. We're going to learn how to assess what I refer to more generally as measurement invariance, but synonyms for these terms, factorial invariance, not like factorial ANOVA, but more like factor, like latent factor invariance. Or also measurement equivalence, which is the way that I would describe it to a layperson. Invariance is a non-intuitive technical term. Equivalence is an easier way to describe it. The big idea is that the set of techniques we're going to talk about are designed to investigate to what extent the item parameters, so the measurement model parameters, whatever they are, work the same way across either different groups of people or people under different conditions. So say in longitudinal data, under different manipulations, like if you give someone the same set of items with two different sets of instructions, for instance, you might want to know whether the item parameters are the same across all of these conditions. This more generally is known as a test of measurement invariance. So time can be a condition, yes. Yes. There's the way that you set up the model differs depending on whether or not it is a repeated measures group or a between subjects group. But this exact same set of ideas and procedures apply. So there's sort of two levels of this that we'll talk about. There's the measurement model and the structural model. Having the measurement model function as similarly as possible is a precursor to being able to make meaningful comparisons across groups or across time. You want your item loadings to be the same. You want your item intercepts or thresholds to be the same. You want your item residual variances to be the same. That way you can say that the items are measuring the traits in the same way. Then you can talk about whether or not different groups of people have higher factor means than each other, whether they have more variance than each other, whether the patterns of covariance are different, or things like that. So measurement invariance versus structural invariance. Is this related to moderation is a question. That's a great question. Yes, it is. So the idea of moderation would be the extent to which your conclusions depend. You can think of these models as ways of testing an interaction between group and item, where group is a moderator of item. The models that I'm going to show you are specific to conditions in which group is a discrete variable. So moderation by group as a categorical distinction. There are models that allow you to examine the same sort of invariance across continuous variables too. So for instance, if you had age, you had the same items administered to people of different ages and you wanted to know if the items function the same way for people of different ages, rather than cutting up age into young versus old or something like that, you can actually treat age as a quantitative variable. There's one or two articles on your reading list about that, a technique called moderated nonlinear factor analysis. It's a terrible acronym, but it's the idea of building a regression model as opposed to an ANOVA type model in looking at moderation. So thank you for the segue. Yes, indeed. If the items function the same way across groups, then what you can say is that the only reason for differences between groups is because of their traits. It's not because of some sort of other artifact. That's the objective of this set of techniques. So these types of models are necessary whenever you are trying to extend the measurement to a type of sample in which it was not intended. So for instance, if you have a scale that was developed in English and you want to test the Spanish version, you may get a sample of respondents from both places and make sure that the items are working the same way in different languages. If you have a measure of, let's say, depression that was created for college students and you want to try to give it to adolescents, something like that. In high stakes testing, the idea that the items should be fair and unbiased is a really big deal. So you want to make sure that the items are not more difficult for certain kinds of people or less discriminating for certain kinds of people. And in that context, especially when your item responses are categorical, this same set of techniques is known as the inverse. It is differential item functioning, which corresponds to non-invariance. So if you have items that work differently, that is what's known as diff, or differential item functioning. If the items work the same way across groups, that is invariance. So non-invariance is differential item functioning. And by the way, non-invariance is probably the worst possible way we could phrase that, right? Non-invariant as opposed to just different or same. But that is the way that it's talked about, for better or worse. More job security. So measurement invariance then concerns how the indicators, your items, measure the latent trait across groups or times or conditions. So in the context of CFA, your item parameters would be your factor loadings, your intercepts, and your residual variances, as well as any residual covariances that you had to add to your model to address unaccounted for dimensionality. Can I say that one more time? The invariance diff part or the item parameter part?
The invariance diff part.
Okay.
Sorry.
Yep. So if your item parameters are the same across groups, the items work the same way. That is invariance or non-diff. If your items work differently across groups, that is what's known as non-invariance or diff. So same is invariance, non-diff. Different is non-invariance, diff. Did I get that right? That's another close the eyes and concentrate set of language. Only statisticians could come up with such convoluted terms that mean same or not the same. But in CFA, the things that we're going to be saying, same or not the same, item intercepts, item factor loadings, residual variances, and any covariances. And we go through a series of tests on those. That's what's known as the measurement part of measurement invariance. Then, as an option, because you may not always be interested in this, but you could, continue on to test what's known as structural invariance, which concerns the parameters related to the factors, whether the factor variances are the same across your groups, whether the factor covariances are the same, whether the factor means are the same. And in contrast to measurement invariance, which we always want to hold, structural invariance may not hold. Structural invariance is a legit hypothesis because your groups may be different, and that's okay because they're different in their factors, which is the level of inference that we want to have. We want to make sure that the items work the same so that we can talk about factor differences as real differences. That's the idea. So how to set this up? That we'll get to in 1 second. One more question. So hypothetically, if the literature says a specific trait does not change over time and you want to challenge stability, then you want variance. You want non-invariance. Yes, if variance is non-invariance. Yes, so if the literature says that these two groups are the same and you don't think that's true, then you want structural non-invariance. But in order to be able to say that it's about the factor and not about the items, you have to clear all of the hurdles of measurement invariance to get to the structural part. Great questions. Okay. So how to set these up then? If your groups are independent, so if you have samples of different people who are unrelated to each other, then the way this is going to work is by estimating a factor model separately for each group, but simultaneously. So the first model that we'll estimate is one in which each group gets its own version of everything, but it's simultaneous. And then we will test how a series of successive constraints for each type of parameter make the model fit not worse or worse. So the only way that we would know if an item loading, say, differs between groups is if it's being estimated in each group simultaneously but separately. And then we can compare that to a model where the loading is forced to be the same across groups. So separate but simultaneous factor models per group is how it works if the groups are independent. If they are dependent, so the same people measured over time across different conditions, if you have like parent report, child report, dyadic data, anything like that, where there's an association between the sets of factors, they have to be in the same model. So you would have to have, say, a factor for time 1 and a factor for time 2, and those factors would get to correlate. You cannot use the multiple group separate but simultaneous approach if there's dependency between your groups. It's just as wrong as doing a regression on dependent data or longitudinal data or anything like that. So what I'm talking about then, I think I've got a picture. Yes, I do. This is from your textbook. So for instance, if I wanted to make sure that job satisfaction as my latent trait was measured the same way at 2 different occasions, the way that I would set this up is to have a time 1 factor and a time 2 factor, and they would automatically get to have a covariance, because how you scored on your trait at time 1 is likely to be related how you scored on your trait at time 2. The other part that is usually automatically included are residual covariances between the same item over time. So that's something that you automatically can stick in your model. No one will yell at you, and they just stay there the whole time. So the examples that I'm going to show you, the first one is going to be a multiple group model for independent groups, separate but simultaneous models, and the second one is going to look like this, but it will have 3 occasions instead of 2. So we'll get a chance to see both types of setups. All right. Good so far? Okay. Now the nitty-gritty. So we're heading back to CFA this week. Next week, we will return to IFA and IRT. So we're back in the world of a linear relationship of your trait, which is now going to be called factor, in predicting your item response directly. So no link functions, none of that, and residual variance for each item is again an estimated parameter. So we have our picture here. Just to remind you, the measurement model in CFA concerns the factor loadings for each item, the residual variances for each item, and the intercepts. The structural model is the factor variances, covariances, and factor means. So the process of testing invariance in CFA is something that pretty much everybody agrees follows the same set of steps. There's really no controversy. There is only one way to do it. The only possible source of disagreement would be whether or not you need to do this first step, which I've labeled as 0 here, which is an overall omnibus test as to whether the saturated model differs between groups. Do you remember the saturated model? H1, if you let all the item variances, covariances, and means be whatever they want, you can do a hypothesis test as to whether you force all of those to be the same across groups, whether that makes the model fit worse than letting them differ across groups. So this is what's known as an omnibus test. If the model fits not worse, people would say, you're done, you have invariance, game over. A lot of people, myself included, don't see this step as terribly useful. Because think about how many parameters you're testing at the same time. You could have little pockets of differences across groups that the overall test would wash out because you're testing so many things. So I don't see this as useful, and I'm not going to do it. So we're skipping step 0 and we're starting with step 1. So I will describe to you in a sort of general sense what this would look like, and then you'll get a chance to see it in a specific example with items measuring depression. So here's an example just to navigate through the slides. Let's say that I have a model that has 2 factors, 3 items per factor. It has what's known as simple structure. Do you guys remember that term? Each item loads on only one factor, so no cross loadings, no bifactor fancy models, none of that. Just simple. Because this is also simple, right? Don't you love it when people like use words that are condescending as part of their definition? Like simple linear regression, simple structure. Yeah, never be the person who says something is obvious or clearly or simple in your papers. I see too many of that, and I call the authors out on that all the time. Like, how about we don't piss off our readership by telling them that this is obvious or clear? Because to someone out there, it's probably not. But they call it simple structure. Anyway, 2 groups. If this is my factor model and I want to test invariance across 2 groups, and my groups are independent, so multiple group, separate but simultaneous models example, the possible number of parameters that I have, here's the formula. The number of indicators times indicators plus 1 divided by 2 plus indicators. If I have 6, I have 27 total parameters I could estimate. That's the sum of the indicator means, variances, and covariances within a group. I got 2 groups, and so there's total degrees of freedom 54. That's what we're starting from. The first question is what's known as configural invariance. And by the way, these words that are in the quotes, these are words that people use. Like if you use these words, people will know what you're talking about. But to be absolutely clear, I always put in a parenthetical that tells in more layperson language what that means. So configural means, does the same basic factor structure hold across groups? Like, do I have a 2-factor model where these items load on factor 1 and these items load on factor 2? That's configural. So the test of that is nothing more than taking the model that you fit overall and fitting it within each group simultaneously. And then you'll get an overall set of fit statistics that describe the fit of the model to both groups at once. And if the model fits well enough, then you have configural invariance and you can proceed. If it doesn't, then it doesn't make sense to go on. So let's say that I have one group in which I have items that are best described as a three-factor model, and I want to test invariance against another group that only has a two-factor model for the same items. Doesn't make sense to go forward because what the factors mean conceptually is not the same thing if different items measure them. So configural is like basic factor structure. There are ways to sort of trick it into becoming the same. So in other words, if I have a three-factor model versus a two-factor model, another way to describe my two-factor model is as three factors, two of which are perfectly related. So you can kind of bend the rules a little bit by allowing three factors, but one of them they have a perfect correlation in one group but not the other. It may be the case that that correlation comes off of perfect once you do other modifications to the model. You can have error covariances that are part of one group and not the other. People would be okay with that and still call it configural. But this is as good as it gets. So unlike what you do in your homework where you're trying to make your model fit better, like you're trying to get to the point where CFI and TLI and RMSEA and everything likes your model, and so you're adding stuff, you might add another factor or add an error covariance or add a cross-loading to try and make your fit better, and then you're like, yay, it fits well. This process is exactly the opposite. We're going to take stuff away and see if it's not worse. So like, do you know the game Jenga? There's like wooden blocks and you make a tower out of them and you stack the whole tower up and then you slowly pull the block out and try and not make the tower not fall down. This is Jenga. That's what we're doing here. The configural model is the original tower of all the blocks in place. It's as good as it's going to get. It's as stable as it's going to get. And we're going to take stuff out and hope it doesn't fall down. To test the pieces, to take stuff out, we are going to do nested model comparisons. You guys already know how to do this. So if we are using maximum likelihood in a CFA context, MLR for robust maximum likelihood, we're going to do the -2 log likelihood difference. If it's the robust version, you have to incorporate the scaling factors. So along with the examples for this unit, I have spreadsheets. So you can use those to do your own invariance calculations, but it's showing where all of the numbers that I'm going to show you came from. But if it's MLR, it's something you can do yourself. If it's diff test, which for IRT or IFA models, that's something that M+ has to do for you. So we're returning back to the you test the differences in the HO models. So in these models, H1 is always going to stay the same. We're comparing alternative versions of the HO because you are the hoe. So you start out with your configural solid block tower, and then we compare a model that has fewer parameters to which you've added constraints as the new HO. And the goal each time is not worse. So we want, ideally, to be able to make all of the item parameters the same across groups and not hurt fit. If we can do that, then we have invariance. We can say that the items measure the trait in the same way across groups, and having that measurement invariance gives us a license to then focus on how the groups differ in their factor scores. Real differences at the factor level. That's what we want to get to. So if you think about how statistical power plays out in this context, it is not the usual way. Do you want to have a lot of people or not a lot of people if you're hoping for invariance? Not a lot of people. Yeah, because power is the chance to detect a decrease in fit. So the more people you have, the easier it is going to be to find that you made the model worse by constraining the parameters to be the same across groups. So those of you in large-scale data sets, those of you who have thousands of people, you are never going to have non-invariance. You're not. Everything is going to become a significant decrease if you have a ton of people. You're going to have to argue on the basis of some kind of effect size that the difference in the parameters is practically non-significant as opposed to statistically non-significant. There's not a lot of convergence on how to do that. You will see different strategies using changes in, say, CFI or RMSEA, but focusing on the differences in the parameters, right? If I have a factor loading that's 1.2 in my one group, but it's 1.19 in another, and that's a significant difference, it's hard to argue that that's not really the same factor loading. So those of you who have small samples will have an easier time finding invariance because that corresponds to a lack of power to detect differences between groups in what the item parameters should be. Okay, does that make sense?
Can I ask a question?
Please.
How would we go about finding the right number of people to power something like this?
You would have to approach it either from a power analysis where you would have a designated effect size that you're trying to calculate sample size for. So you'd have to find some way of expressing the difference in your loadings or your intercepts as in some kind of effect size metric. Or you would approach it from the opposite perspective, which is known as a sensitivity analysis, where it's like, okay, I got 100 people. What can I do with that? And then you work backwards to figure out what the minimum detectable effect size would be.
Got it. Thanks.
Sure. There's not an easy answer. You want a lot of people, but not so many that it's ridiculously overpowered. So however many that is, I don't know. So we got our Jenga tower. We're going to start pulling the pieces out. That's what we're doing. Okay, are you with me? Okay, let's do this. So here is just to review the difference in -2 log likelihood. It is not the straight difference. It is the scaled difference. So you have to have the scaling factor that shows up for the robust maximum likelihood estimator in your output as part of your calculations. I have a spreadsheet that does that for you. If you don't have robust maximum likelihood, that is the same as using a scaling factor of 1. So the formula simplifies to the regular ML -2 log likelihood difference in that case. By the way, this procedure more generally is known as a likelihood ratio test. You can either think of it as the ratio of likelihoods from a model with fewer parameters over a model with more, or you can think of it as a difference in log likelihoods. So if you take the log of something, what used to be division is subtraction, and what used to be multiplication is addition. So this is either a likelihood ratio because you divide the likelihood of one model versus another, or it's a log likelihood difference. So I say this because I've seen people write things like log likelihood ratio test. Think about that. That doesn't make any sense. If it's a log likelihood, it's a subtraction. If it's a regular likelihood, it's a division. So even though the formula has subtractions in it, it's because we're working with logs. The title of this procedure is likelihood ratio test. You will sometimes see people call it a chi-square test, but that's not very descriptive because that chi-square test goes with a lot of things. But this result, the difference in log likelihood corrected for the difference in scaling factor, is supposed to be distributed as a chi-square. And the degrees of freedom is going to be the difference in the number of estimated model parameters. So in our context, the degrees of freedom for these comparisons is going to be the number of constraints. So how many parameters did we save by constraining things to be the same across groups? And this same process would be used in full information maximum likelihood for IRT or IFA models as well. Alrighty, so here's my configural model, the full tower with no blocks removed. So the notation that I'm using then is a slight difference on the ones that I've used before because I'm adding a second subscript to differentiate group 1 from group 2. So in this model, I have what the item level equations would be for group 1. So the first item for group 1 that varies across subjects is predicted by its own intercept for item 1 in group 1, a factor loading for item 1 in group 1 that is a multiplier of the factor score in group 1 that varies across subjects, and E is the residual for item 1 in group 1 for subject S. And so if I go across over here, there's a 2 in the second place to denote that this is the term for group 2 specifically, but it's still for item 1. So each item gets its own intercept. Each item gets its own factor loading. If you had a model in which an item had more than one factor loading, then it would get each individual factor loading estimated separately across groups as well. And the E's here each have a different variance across items and across groups. So if we count up the number of estimated parameters, there's 54 total. So there's 27 possible in each group if I count up the number of item means, item variances, and item covariances for the 6 items within each group. So what have I spent? I have 12 intercepts, 6 in group 1, 6 in group 2. I have 12 error variances, 6 in each group. I have 12 factor loadings. I have 0 factor variances. So sigma squared F is my symbol for factor variance here. Why don't I have any factor variances estimated as part of my tally? Who wants to tell me? So this is a review at the same time we're working on taking apart our Jenga tower. Why don't I have any factor variances estimated here? They are set in identification? Yes, indeed. So the only way that I am allowed to estimate all of the factor loadings is if I fixed the factor variances for both factors in each group. So there's 2 factors times 2 groups. There's 4 factors in total here. All of them have to be fixed to 1 for this model to be identified. I could fix it to 10 if I wanted, but fixed to something that's not 0. That's a positive number is the key. I do have 2 factor covariances. So within each group, factor 1 and factor 2 get to have a covariance, and those are separate across groups. Last but not least, I'm using the K looking thing, I think it's kappa maybe, for factor means. And why don't I have any of those? Yeah, they're 0. Those are also fixed. They're fixed so that I can do what? Test the model? True, but not where I was going. Looking for the correspondence. So if in order to estimate all the factor loadings, I have to fix the factor variances. In order to estimate all the what's, I have to fix the factor means. Which item parameter corresponds to factor mean? Not loadings. Loadings go with variances. Mu, yeah, the intercepts. So the rules of identification, if you're going to estimate all of the individual item intercepts, the factor means have to be fixed to 0. Fixed to whatever, but 0 is the most common thing, and it's convenient for most purposes. So means at the factor level correspond to intercepts at the item level. Variances at the factor level correspond to loadings at the item level. This is going to be important because as we put constraints on the item parameters, we're going to have to free the corresponding factor level parameters to avoid putting constraints at the structural level. So let me say that again. In terms of identification, in order to estimate all of my factor loadings, I have to have fixed all the factor variances to 1. In order to estimate all of the individual item intercepts, I have to have fixed the factor means to 0 in both groups. I am confused why we have 2 factor covariances because there's 1 in each group. Each group has 2 factors, 1 covariance between the 2 factors. So it's in both groups. So at this stage, it's as if we're fitting a separate model in each group completely. Just we're doing it simultaneously so that we can get a sense of their combined fit. So at this stage, the factors are identified separately within each group. They are not comparable. So a factor score of 0 in group 1 has absolutely nothing to do with a factor score of 0 in group 2. They're not on the same scale. They do not correspond in any way. They are separately identified. That is critical because people often try to make comparisons when they're not justified. They're not on the same scale yet. We have arbitrarily set the scale to 0, 1 in each group separately in this configural model. What follows is going to slowly put them on the same scale in different pieces. So loadings go with factor variances, intercepts go with factor means. Okay, other questions? So this is my configural model. It's as good as it's going to get. The next step goes by a couple different names. Conceptually, what we're going to do is test the loadings. Loadings come first. So we can call this metric invariance. It is also known as weak invariance. Weak in contrast to strong and strict, by the way. These are adjectives that have very special meanings. Metric means loadings. So if I were writing this up, for instance, the write-ups that I've given you in your examples, we then tested metric invariance, parenthesis, i.e. equivalence of the loadings across groups, right? Help a reader out. So do they have the same factor loadings? A point of common misconception at this stage. This is not the same thing as testing tau equivalence. So do you remember tau equivalence or Roche model or true score equivalence? The idea that the slopes were equal across items? That's not this. So in those constraints, when we were testing whether, say, a 2PL fit better than a 1PL, all of the items shared a slope within the model. This is item 1 has the same slope as item 1 in group 1 and group 2. Item 2 has a different slope than item 1, but it's the same across groups. So it's still a congeneric factor model in that each item gets its own slope, but the slopes are constrained to be equal for the same item across the 2 groups. That's what we're doing. Okay, with me so far?
Can I ask a clarifying question?
Please.
So the idea is that it's different because we're fitting 2 completely separate but simultaneous models. Is that why it's not a tau equivalent? It's because we're 2 separate groups?
It's not tau equivalent because within a group, the items get different slopes.
Okay, but we're about to constrain the slopes across groups, but differently across items, right?
The slopes can still differ across items. Item 1 can
and that's all that tau equivalent means. Okay, yes. Gotcha.
So tau equivalence is item 2 is just as good as item 1 is just as good as item 3. That's not this. Item 1 can be different than item 2, but item 1 is the same item 1 in both groups. So the constraints are across groups, not within groups. Critically, though, at this stage, we are freeing the factor variances in what is known as the non-reference group. So in the way that these models are set up, we have to designate one of the two groups as the reference and one of them as the alternative or the not reference. If you had three groups, you'd have one reference and two alternatives. The concepts would be the same. So what's going to happen in terms of identification is that the reference group's factor is still going to be nailed down to 0, 1. The mean is 0, the variance is 1. In the alternative group, the variance is going to be free. Because what we are saying is that all of the differences in what we would perceive as the loadings are actually differences in the factor variance instead. So whatever loading differences would have been there can be explained by letting one group have more factor variance than the other. So we can't forget that step, otherwise we're forcing a structural constraint and a measurement constraint at the same time. So to put it a little more concretely, the bolded loadings here are showing the newly constrained parameters. So the lambda 1 is the loading for item 1. It's still a different number than lambda 2 within each group, but lambda 1 for the first item is the same in group 1 as it is in group 2. So we have saved 6 factor loadings. We used to have 12, now we have 6. But we have also added parameters at the same time at the structural level. So we are now estimating differences in the factor variance for the alternative group. That factor variance, those two factors, each have a variance that is free to be whatever it wants in the alternative group. We have to do that. So what we're saying is that the only reason that the loadings were different is because the factor variances are different. And once we allow group differences at the factor level, everything shakes out proportionately at the item level. That's what this step is testing. So it is a total savings of only 4 degrees of freedom, because even though we've cut down on 6 loadings, we had to add back in 2 factor variances in the alternative group. The intercepts and the factor means are left untouched, though. They're still on separate scales across groups. Okay. Factor variances also untouched. Okay, with me? Now, do you want to see the next 2 steps in here, or do you want to see what this would look like in M+? Anybody care? So I could go either way. One vote for M+? It's like those choose your own adventure books. Did you guys ever read those? There was a series of books where you could decide for the character what to do, and if you picked like one decision, it'd be like skip ahead to page 18, and if you pick the other decision, go to page 30. Yeah, it's like that. It's you choose your own adventure. Okay, only one person cares, 2 people cares, 2 votes for M+. Let's do it then. So let me show you an example that comes from your textbook. So this is from the Brown 2015 book. It is an analysis of 2 groups, men and women, each of which is exactly 345 people. In other words, pretty sure this is fake data. But that's fine. The other way I can tell that this is fake data is that he came up with a 9-point scale so that the items would be pseudo-continuous. So continuous enough to fit a CFA model, I think, was his intention. And these are items that are supposed to measure depression, where higher scores mean that you are a more depressed individual. And the question is whether or not these same items work the same way in measuring depression across men and women. So I'm going to show you how to do this in M+, the long way. So here is a caveat. Much like everything else in statistics, I'm going to make you do it the long way so that you understand what's going on under the hood. There is a shortcut that you can use. but I am deliberately pretending that it doesn't exist so that you will know what it is doing for you if you invoke the shortcut. When we get to IFA models, the strategy that I'm going to present will actually differ from the shortcut because I disagree theoretically with what they're doing. So that's my right as an individual to have my own opinion, but I'm not going to show you the shortcuts. I'm going to show you how to do it sort of the long way, even if it's more code, because it's clearer what's actually happening under the hood with that caveat. So we're back to the variable option where there's no categorical. So everything about the code looks the same as what you're used to. I have a person ID column. I have a grouping variable that is it's labeled sex is what he labeled it, and then 9 items. Use variables here. So this is important. Use variables allows you to tell M+ only to use certain variables in your model. If you forget use variables, it's going to put in everything, including person ID. And it will put in all of the other variables as uncorrelated. So they'll just be like floating out there, making your model fit terrible. So if you ever have a model that's like completely horrible fit and you're like, what happened? Check this. Check to make sure that you didn't forget use variables. Because models with variables like ID just floating out there uncorrelated are not going to fit well. Here is a new command that we have not seen yet. Grouping equals. That's how we tell it how to categorize our cases. So grouping equals is used in CFA invariance analyses for multiple groups in which you're fitting separate but simultaneous models for each group. It is not used in models for dependent groups in which you would have multiple factors in the same model instead. So these men and women are separate people. They're not couples or anything. So this is 2 independent groups in this example. And your output will have labels in them that you provide here as to which group is which. So you'll have group 0 output and group 1 output, and you can add what the labels are to help you remember what 0 and 1 mean in this context. It doesn't matter who you put as the 0 or the 1, that's up to you. It'll pick the lowest group as the reference, so if you want to switch it, you would need to make a new variable in which they're switched. As usual, make sure to tell it what your missing data code is. We're using robust maximum likelihood estimation. I have added the modification indices. Those are going to be important because they are going to be able to tell us which constraints hurt our fit. It's going to be our clue as to which loadings can't be constrained and which ones can. So modification indices are used here in a different way than they're used in regular model fit testing, because we're going to look only at the ones that pertain to the constraints that we've placed. So all of this setup would be the same for all the models I'm going to show you. The only code that I'm going to show you is what starts from here. And the full output files for each of these runs is available inside the zip folder. So this handout has sort of the highlights of the output, but the full thing is available for download. Okay, questions on the setup so far? So understanding what is going to happen with the code requires this. Whenever we see model, that is us telling M+ what the factor model should look like for the reference group. We're also going to have a separate model statement for each of the alternative groups. So you'd have one for each group in models that have more than 2 groups, just one here. And the role of this subsequent statement is to tell M+ how the alternative group's model should differ. So sort of the default position of M+ is that everything is the same. So you have to override that constraint that everything is the same with code. And then we will selectively make everything the same to test the layers of constraints. So in this example, I am denoting women as the reference group. So all of these statements over here on the left-hand side refer to what the factor model looks like in the women group. So my factor is going to be called depress. Can you guess why I didn't name it depression? Jing, is this a gesture for me? Yes, too long. Yes. You get 8 characters because the interface here is straight up 1985. You get 8 characters or fewer, so it's depress and not depression. Item 1 to item 9. I have preemptively added my labels here. Right now, they're not doing anything but being labels. Later on, each of these labels will help me place constraints on what is the same between women and men across groups. So each of my items is going to have an estimated factor loading. Let me zoom in here. Here's an opportunity for review. This star right here, do I need it or not? I do need it. What would happen if I forgot it? The first item 1 would have its factor loading fixed to 1, and all the other loadings would still get estimated. So in order to estimate the model in the way that I want it identified, which is factor variance 1, all the loadings estimated, I need the star. So the star is actually really only here for making sure that item 1's loading is estimated. The others would have been estimated regardless. When I teach M+ code, I get in the habit of putting stars everywhere there's estimated parameters, just to be clear. By the way, if you want to provide start values, if you put a number after the star like this, that's treated as a start value. So start values are used to speed up estimation in models that are very complicated. Yes, later in the semester, I will show you how you can generate start values very easily with an option in M+, but just in case you're curious. Also, if you're using M+ to do simulation research, where you know what the right answer should be, you can put it in like that, and then in the output, it will tell you how far off from the right answer your parameter estimates were on average and stuff like that. So
can I ask a
stars needed.
question?
Yeah.
So when you just put that 2 behind the star, then does it mean that you estimate all the loadings as 2? Okay.
I estimate them, but I start them at 2. So 2 would be a start value in that case. It's not something that you would need to do in many types of models, but particularly in models where you're using numeric integration that take a long time, providing start values is a way to speed up the estimation process. Would you still get the same estimate? Yes, with a question mark behind my answer. In theory, yes. More generally, in providing start values to different packages, not always. I have seen models not converge for some start values that would converge for others. Would you ever start different items at different start values? Yes. Yeah, so more generally, if you were going to put start values in, you would do so for like each item. For instance, like item 1 starts at 1.4, item 2 starts at 0.8, and so on. If you were going to go to the trouble to put start values in, they should be specific. But just as an FYI, if you mean to constrain something to fix it, that's an @ sign. @ is how you fix it. Star is estimated still. Okay. Next line, things in brackets are means or intercepts. So these are item intercepts. For just a week, we get away from the thresholds. Hallelujah. It's an intercept. It's the expected outcome when the predictors are 0. It's such a familiar and comforting place. But we're going to have 9 of those. We're also going to have residual variances. So in these models, residual variance is separately estimated because these models are for normally distributed items. So in IRT and IFA, residual variance is not a thing. It's not an estimated parameter, but it is in this case. In this particular example, previous analyses had indicated that items 1 and 2 want to have an error covariance between them. So I have added that with this with statement, and I have a label for that. So if I look at the content of the items, depressed mood and loss of interest apparently have something in common beyond the depression latent trait that they're supposed to be measures of. So whatever that something is allowed to contribute as an error covariance. And then last but not least, making sure that the factor is identified. So when I list the factor by itself, that's referring to either its variance or residual variance based on the context of the model. That is fixed to 1. The factor listed in brackets is its mean or its intercept, and that is fixed to 0. So the factor is identified with these two statements right here. The alternative group code looks exactly the same, but there's no labels. So remember, the alternative group, the men in this example, the role of that model statement is to describe which parameters need to be different between the two groups. So by listing everything, I'm saying make it all different, because this is my configural model where I just want everything separate but simultaneous as my best fitting baseline to which I'm then going to apply constraints and see if I make the model not worse. So it's the same code minus the labels. So separately identified factors in each group. Okay, questions on that much? Why don't I label? Because what's going to happen is that I'm going to borrow these labels and attach them to the alternative group, and that's going to make the loadings the same across groups. So I'm going to use the labels to create same constraints. And so therefore they will be not just labels, but constraints, but not yet. That will happen in each successive model to follow. Okay. Very confused. It's okay. The objective at this point is separate but simultaneous models. That's what we're doing. By not using the same labels in both sides, I'm keeping everything separate. So you'll see what happens in the models that follow. Once I start putting the same labels on both sides, those parameters will be forced to be the same across groups. I'm not doing that yet. I am doing step 1. Yes, this is my configural invariance model. Does a single factor of depression fit in both groups? That's my baseline. That's the first thing I need to find out before I can go further. So this is my configural invariance model. It has 56 parameters that have been estimated. And here is my log likelihood for my model. That's the height of the model across the two groups. The H1 model is my best possible model. The difference in fit of my HO model for the single factor relative to the best model is the 94 down here. So I have a significantly misfitting model in an absolute sense, but if I go over to the fit statistics, they're reasonably happy with the model. So this is a good enough place to start. So note that the only place that it tells me about each separate group is right here. There's an entry called chi-square contributions from each group. So how much of the total model chi-square, the difference in your model relative to the perfect model, how much of that is allocated to each group? And this will be a function of sample size. So it's only going to be equal if the groups are the same size. So we have a reasonably well-fitting model if we let each group have its own factor, and that's a place to start. So is H1 the women the reference and HO is the men? No. H1 is the saturated model summed across groups of each group's items, means, variances, and covariances. What is the height of the data if we just let the items be whatever they want in terms of their mean, variance, and covariance? That's still H1. HO is what the single factor model predicts in each group combined. So HO is the single factor model for each group at the same time. H1 is the best possible, everything gets to be what it wants model in each group at the same time.
Lisa,
Yeah.
so is our model different from H1 model? The only difference is the residual covariance here?
Your model is different from the H1 model in the H1 model has 52 more degrees of freedom that you could have spent and you didn't.
Okay.
So there's nothing in here that is comparing the men and the women.
No, yeah.
This is single factor model versus perfect model.
Yeah, I just wonder what's the difference between our configural invariance model between the saturated model here.
This chi-square test tells us how much shorter our single factor model is than the perfect model. That is the comparison of HO to H1. So this is the one comparison that M+ will do for you each time.
Yeah. Oh, okay, thank you.
Okay, so from here on out, our comparisons are relative to the other HOs. H1 is sort of not relevant from this point forward. The residual covariance is in each group. I was checking to make sure that was the case. Yes. Okay. So I know this is confusing because there's a lot going on at the same time, but at this stage, we're not yet comparing groups because we let each group have their own version of the model. There's no constraints whatsoever.
Can I ask a question?
Mm-hmm.
So is it a single factor model just for women? No, just.
It's a single factor model for each group, for one for men, one for women, estimated simultaneously.
Okay.
I'm trying to think if there's any other way that I can do an analogy. Like if you do a path model, if you're trying to fit like a multivariate analysis where you're predicting a bunch of different outcomes, you can have a separate regression model for each outcome, but you get all of them at once in a path analysis. So this is kind of the same idea. It's a single factor model for the men. And by the way, or women is the reference group, sorry. So like here's the women group's parameters. On the right-hand side, I've pasted in the men's parameters. So each group gets their own set of factor loadings, their own set of intercepts, their own set of error variances, their own error covariance, and there's no factor parameters because there's only one factor in this case. So I'm working from sort of two different examples. This is a single factor model, and in the PowerPoint slides, I'm trying to describe how this would be extended if you had two factors. The factors have to be identified, each factor in each group. So both men and women contribute towards the HO even though it looks like two different models. Yes. It is two different models. So I've got two sets of parameters here. So for instance, the factor loading for item 1 in the women is 1.25. The factor loading for item 1 in the men is 1.024. And these factor loadings work together to describe what the model says the covariance should be between the items. So the covariance between items 1 and 2 in the women should be these two loadings multiplied together, whereas the covariance between items 1 and 2 in the men should be those two loadings multiplied together. We can go back to the original data and see what the actual covariance between items 1 and 2 was in each group, and the model fit test tells us how far off the predicted covariances are between the items relative to the real ones. So the sum of all of the offnesses, so to speak, is what the global chi-square test is telling us, is does the single factor model fit these 9 items separately but simultaneously in each group? Okay. So here are the solutions. These are separate. I know I keep saying that, but I'm trying to hammer the point home. They're on different scales. So the mean is 0 in each group. So I have no way of knowing if men are more depressed than women or if women are more depressed than men. This model can't tell me that because they're separate and simultaneous. They have nothing in common. The point of this model is to provide the best fitting baseline against which to compare what happens when we slowly start forcing each type of item parameter to be the same. First the loadings, then the intercepts, then the residual variances is the order that we'll put them in. The other thing that I'm trying to do with the results is foreshadow what's going to happen. So here is a picture. I just threw the item loadings into Excel of what the loading looks like for each item across genders. So the red lines are all different heights, meaning this is not a tau equivalent model. Each item gets its own loading. The blue lines are all different heights too. And the difference between red and blue is allowed to be whatever it wants. So what we should see is that if the reason for these differences between the loadings is at the factor level, then if we force the loadings to be the same across groups, then that should translate into a difference in factor variance. So invariance is foreshadowed by proportional differences here. So the pattern, it looks like the items work better in women than in men for items 1, 2, and 8, whereas some of the others look like it's the opposite pattern. So we're looking to see, this is trying to foreshadow, I should say, whether or not the differences between the loadings can be ascribed exclusively to the factor level. That's the next thing that we get to figure out. So the metric invariance model is accomplished with this one change. I have added the label L1 to L9 onto the men side. So now, in addition to labeling the loadings L1 through L9, I am forcing them to be the same across groups. That's a metric invariance, weak invariance constraint. And because I'm doing that, I'm freeing the factor variance in the men group. So it's being estimated. So that is where we will pick up next time. So questions before we adjourn? Not today? All right, well then office hours start now. Let me know if you need anything, and I'll see you Thursday. Bye, folks.